Hello and welcome to this video on isotopes. This follows up from the video on deducing the number of protons, neutrons and electrons in atoms. So today we're going to look at a periodic table. It's going to help us anyway. And the one I'm using is from OCR, and this is their A-level paper. So if we look at the periodic table, one of the problems we get is that, when trying to work out the number of neutrons anyway, is that the mass numbers aren't always whole numbers. So, for instance, if we take a look at chlorine on the periodic table, chlorine has an atomic number of 17 and a mass number of 35.5. So if we work out the number of protons, we'd have 17. There's no charge here, so the electrons is also 17 because they have to balance out. The number of positives has to equal the number of negatives. And neutrons, well, if we take this mass number here and minus 17, we get 18.5, which we can't have. You cannot have 0.5 of a neutron. So this, or at least this bit, can't be done. So why do we have 0.5? And that's because of the isotopes of chlorine. There's not just one version of chlorine. There's actually two. Oh, there's two stable versions. We have chlorine 35 and chlorine 37. And we take a weighted average of these to get 35.5. And at the latter part of the video, I'll go through that calculation. Why do we not end up with 36 then for its atomic mass if it's an average? And we weight it slightly. We can look at this with another example. I'm going to take three isotopes and they're all the same element. So they'll have protons, neutrons and electrons. That's a P. That's terrible, isn't it? There we go. There's a P. So they all have 6 protons. They're all the same element. So if they're the same element, they're always going to have the same number of protons. It's got a bit of glare coming on there. The number of neutrons I'll come to in just a sec. Number of electrons. Now these are, although we call them isotopes, these are also atoms, so there's no charge on them. So this one, because it's got 6 here, we'll have 6 electrons. The positives has to balance out with the negatives. So they're all going to have 6 electrons as well. Now the neutrons are going to change. And this is what an isotope is. So atoms of the same element have got the same number of protons, but a different number of neutrons. So this first one is going to have 6. Second one will have a different number of neutrons, and this third one will have, again, different number of neutrons to the previous two. So the eagle-eyed will have spotted what element this is by the number of protons. You have a look at the periodic table, it'll be the element with the atomic number of 6, which is carbon. And here we have, put down at the bottom, this one is carbon 12. It's got a mass number of 12 with 6 protons. This next one is carbon 13, and this fourth one is carbon 14. So these are all isotopes of carbon. Now, majority of carbon in the world is carbon 12, like 99%. I'm not too sure on the exact percentages, but massively, massively carbon 12. So the number's weighted way towards carbon 12, which is why you get 12.0 on periodic tables. If you've got a more advanced one, it might be 12.01 or 12.02. Because there are these other two isotopes, carbon 13 and carbon 14. Carbon 14, important use is in carbon dating. It helps us date how old dead things are, dead animals and living tissue. These all have the same chemical properties. Really, we only care when we look at chemistry and how it reacts. The electrons are really important to us. Because they've all got the same number of electrons, then the chemical properties are going to be very similar. It's the physical properties that change, and that's because of its mass. So because they get heavier, they move around slightly differently, they interact with other things slightly differently. So that is isotopes, and this is the isotopes of carbon. So each of these are atoms. They're all carbon, but they're the different isotopes of carbon. So we'll have another look at another example of an isotope, and I'll go the other way this time. I'll give you the isotopes name to begin with. So we're going to look at magnesium. Magnesium has 3 isotopes, or stable isotopes. Magnesium 24, magnesium 25, and magnesium 26. And then I'm going to create the same table again. So we've got protons, neutrons, electrons. And we can work out all of these are going to be the same because it's the same element. They're all magnesium. So we look at the atomic number, which is 12. So they all get 12 put on. And the electrons are going to be the same because none of these have charge. They're all the same, 0 charge. There's no plus or negatives after them. So the protons have to match up with the electrons. The neutrons, though, are going to change. So first one, magnesium 24, is going to have 12 neutrons, because 12 plus 12 gives me 24. Magnesium 25 is going to have 13 neutrons, because 12 plus 13 gives me 25. And magnesium 26 is going to have 14 neutrons, because 14 plus 12 is 26. And that is the isotopes of magnesium. Now, again, slightly more magnesium 24 than 25, 26, but not quite as weighted towards its carbon was. So the relative atomic mass, this average we take for magnesium, is 24.3. Now there's some question sheet provided, and you can give that a bit of practice if you want, working out how many protons, neutrons, electrons there are in different isotopes. Now we're going to look at relative atomic mass, or RAN. And that is the numbers that you see on the periodic table. So relative atomic mass, we can calculate by taking the mass of isotope, and we could have 2 isotopes, we could have 50 isotopes. Doesn't matter. I'm going to show an example just with 2 isotopes. So the mass of isotope 1 times the percentage abundance of isotope 1. I'm just abbreviating so I can fit it in. Close the brackets around all of that. And we're going to add that to the mass of isotope 2 times percentage abundance of isotope 2. Ooh, bit of a squiggle there. We could carry on going if we had a third isotope. We'd do mass of isotope 3 times percentage abundance of isotope 3. We'll just keep on adding on and adding on, making sure it's all in brackets, it's separate. So we're going to look at chlorine. Chlorine has 2 isotopes, chlorine 35 and chlorine 37. So these 2 isotopes have different percentage abundances. Of chlorine 35 has 75.8% abundance. Chlorine 37, 24.2%. So we've got here our percentage abundances. This just means if we picked up at random from the world 100 chlorine atoms, 75 of them would be chlorine 35. The other 25 would be chlorine 37. So we get these different amounts all mingled in together. They're not separate. You wouldn't be able to mine separately, go to some chlorine and be able to get some that has pure 37 or pure 35. We can separate them later on. But if we get them from the natural world, these are the ratios they'll be in. we can then use our equation up here. So we do, first of all, our relative atomic mass, put into brackets 75.8 percentage abundance times 35. That's the mass of the isotope. Be careful with this, common problem, or common mistake is people use the atomic number here, but we need the mass number. The atomic number is not going to change between the two. We need the bit that changes. Then 24.2, the percentage abundance of isotope 2, times 37. So if we get a calculator, I've completely forgotten. There's chemists that are going to be watching this going, he's forgotten. We have to, because we've done a percentage, we're going to divide this answer by 100. So 75.8 times 35. Just put that into brackets, otherwise I'll get it all messed up later. Plus, open my brackets, 24.2 times 37. Close brackets. That gives me 3,548. That is not going to be the relative atomic mass. I'm going to divide that by 100 to give me 35.48. I can then check my periodic table. The beauty of these questions is you can always check whether your answer is correct or not by looking at the periodic table, and they have it on this one, just up here, as chlorine 35.5. So I know they've just rounded up here, 48 to 0.5. I know I've done that correctly. And I can always be able to see, have I got the correct answer? Because I can look at the periodic table and go, does that match with what's on the periodic table? If it does, yes. If it doesn't, tough. So below are some practice versions of these as well. So there's two separate sheets today. One, just practicing isotopes and how to work out protons, neutrons, electrons. And then a second one on relative atomic mass and how to calculate relative atomic mass. So answers provided. Good luck with those. Any questions, put in the comments at the bottom.